study. So I would like to show you a picture and ask you, what do you see in this picture? So this is a Cadillac car, but I'm more interested in the systems that we are providing with the car. And the question is, are you seeing a machine made of machines, systems, or are you seeing an experience? And I want to talk to you today, how can we actually transform that activity into an experience, a comprehensive experience? What I've marked with all those circles are the different systems that we are today facing when we are driving a car. So you might see phone calls, navigation systems, climate control systems, cruise control, fuel, and so forth. And today, as you all know, when you drive a car, you are asked to operate each one of these systems. And the main question is whether we can transform our current driving experience today into one comprehensive activity where I am not the one that is being asked to solve all these problems for each one of these particular systems. So what is the main challenge? It's not the automation, on the other hand, it's us, right? You, I, whoever, when we enter a car, are humans after all. And what it means is that we were trained to drive the car, but we are not actual experts. We are not like pilots in a plane. And usually what is more important about us is that by being humans, there are many things that characterize us, like deciding suboptimally. We are not rational players like we could be programmed for doing the optimal thing at every moment. We are usually affected by the context. Different contexts might lead us to react in different ways. And if I ask you what are your preferences for thermal, for example, for being comfortable in a car while the climate control system is working, you might tell me one thing, but then when you are in the car and suddenly you might feel angry at some call you got by the phone or any other thing that happened on the road, you might change your preferences. So it's very difficult to predict a person and its preferences, and that's the reason that these systems are very difficult to solve. Moreover, we would like to have long-term relationships with our users. It's not just a one-time situation where maybe I can fit my system to that particular situation. The car is with you along days, years, months, right? So we want to understand what are your needs a long time, understand the different needs for different contexts, and then be able to program that car so that it gets to you what you really need. And I think a more high-level question, but I think it's very interesting, is that how we all capture automation. So all these systems I show you in the vehicle are automated systems, but what would we really expect from such an automation? Do we expect that system to be perfect all time, under all conditions, or you can understand if the system doesn't work right? So these are questions that are important for us to understand what you really want and what you really expect from any automated system, in particular vehicles, as we are talking in this track. So it's also interesting to note that many studies in automation actually started from the human factors community and their studies. And when you look at their work, it's very clear how automation has evolved a long time. So basically, when they started to work on automation, people that used to operate those automated machines were actual experts. So you have the pilots, you have people monitoring different stations or plants, or people that were trained to operate a specific machine, as different from us, that we could be anyone. Also, automation, when it started, it's very interesting to look at because the first automated machines came to replace physical tasks that were very complex or very heavy for us to do, so the machine was taking that job instead of us. And then whenever the machine was asked to work with that person, usually it was a unilateral relationship. Either the machine was working or the operator was working. They were not really interacting. And now we have AI. AI was developed not as departing from human factors. It's a separate discipline. And the way AI, robotics, human robotics interaction and so forth have looked at those kind of problems is very different. First of all, anyone could be a user. It's not just the very well-trained operators. And moreover, we could work with our AI systems anywhere. It's not just a physical machine, it could be at the digital domain, and even more in the virtual reality domain. And also you can notice that we are talking about multiple tasks. It's not one machine with one task. We are talking about, in the AI community, I mean, we are talking about the value of communication. When the machine is talking with me, what messages it's going to tell me. There are cost functions for all of these points, and how these machines eventually could learn about their users and their users' preferences, patterns of activities, and so forth. And one important, the last bullet is one of the most important, because in opposition to the unilateral interactions, we want to create bilateral interactions. And therefore, our automated agents will be those that also initiate those interactions. It's not just the person monitoring the machine, it's also the machine talking or interacting with that user. So just to summarize this first part of the talk, if we look at the evolution of automation and personalization or human interaction, you can see that users started from being very well-trained experts users into any one of us, right? It could be children, it could be old people, it could be people with any kind of disabilities. Anyone could be using those AI systems that we are talking about. Also in terms of the type of task, as I mentioned before, automated machines just started to replace a physical task that was very difficult for a person. And now we are talking about any domain, physical, digital, or virtual, and all kinds of tasks that could be multiple tasks at the same time with differing contexts. And the automated behavior that we are expecting our agent to perform is not just only dividing the task between now it's the user and now it's the machine. It's kind of bilateral, interactive interaction. So if you look at how the role of the user has changed, when we had the machine, it was an operator. The person was the operator. It was transformed into a user of information when just the internet started, for example. So we were doing mostly information retrieval tasks. But today, we can say that all these systems we are experiencing around us are more like services. So now we are talking about people that are consuming those services. And the question is how we should regard those consumers as opposed to operators that we started with. Whether the interactions should also evolve the same way as our systems evolve and the services evolve. So I'm going to ask three main questions. First of all is how are we going to communicate with the intelligent vehicles? What do we expect from the human and from the vehicle? In order to do that, we need to understand what actually the humans need. As I asked you before, when you enter a vehicle, what is really that you're expecting that vehicle to do for you? What are your real needs when you enter the vehicle? Are your needs like a riding experience? Your needs started even when you started to go out from your home, or are the needs just inside the vehicle? And of course, what are your expectations from those intelligent vehicles? As I said before, it's very important to understand if I am a developer of an automotive system, are you expecting me to be perfect at every point of time? Are you going to understand if something goes wrong and how that interaction is going to evolve? So what are we going to propose in this talk? I'm going to present our work for a couple of years where we develop intelligent agents and adaptive interfaces. And the point of doing those systems is to create a new type of interaction with our users so that users will have higher levels of acceptance of all those advanced automated features, and they will require less interventions from their side. So there is a saying that the best HMI system will be that doesn't require any human intervention, right? If I enter the car and anything is being done exactly as I want, then that's the best HMI. So the idea is that we can use AI methodologies in order to create those agents that will really understand what I need at the right time, provide what I needed, and then I will be happier with those systems. I will have to less interact with that system, and overall, I will be improving the utilization. And meaning, that I think that's also a very important point, because it doesn't matter that we can make more and more advanced systems for the vehicle if our users will not be able to understand what they are doing, or they are not going to use them as they should be. So, for example, you can ask yourself, if you have an advanced cruise control system in your car, are you actually using it? Are you really understanding what it really does for you? So this is the main framework I'm going to use in this talk for 2 domains that we have been working with. So you can think that on the right hand of this diagram, you can see an agent that actually needs to understand in which state the system is in, the agent that is running for us. And it's also able to compute the next state. It needs to be intelligent enough to compute the next state, understanding what's going on. So even if the user is not interacting directly with the agent, the next state is going to be computed, taking into account that the user is in that loop. And by knowing what is the next state it needs to get to, it needs to have a system model. So I'm going to give details for the particular systems we have been working with, but the system model will tell the agent what are the real parameter values that it needs to use in order to actually bring the system to that next state. On the left side, what you see is that sometimes the user might have something to tell us, to give some input. So first of all, we say, we should be looking at those interfaces that really understand people. I don't want to put more burden on you. I want to understand you. So I want to have an intuitive interface so that it's easy for you, and you're not expected to understand what's going on the side of the system. So first of all, we would have to develop those adaptive interfaces, and then I will have also to develop a user model that actually what it does, it will be able to translate those intuitive inputs into the actual system controls that I don't want you to know, but the system still has to know them to perform. So what we are going to achieve is an adaptive agent that has an intuitive interface, is able of logging data from interactions from humans. It learns to predict user needs, learns to interpret those needs into system control actions, adapts in control behavior, and overall it is evaluated by the user acceptance of those systems. In addition to the learning that from AI, this is what we really do. So I think if there is one message that I would like you to take home from this talk, is that we should be looking at automation is not just about the machine, it's about an adaptive and user-centric experience. So as I said, I'm going to give 2 examples. One is about thermal control. It's about climate control systems and how I can cause the level of comfort to increase while your interaction with the climate control system is much more intuitive and intelligent with AI behind it. So this is a kind of canonical climate control system. You might have different climate control systems in your car, but basically what you see is a bunch of buttons enabling you all the type of functionalities you are used to in your car. So maybe this doesn't sound like a very hard problem because you're very much familiar with using your air conditioner in the car. But I want to use this example as an example to tell you how important it is to understand that we don't have to ask our users to know how to configure all these buttons. If you suddenly enter your car and your windshield is getting foggy, I don't have to expect you know exactly what configuration of buttons and functionalities you need to set in order to have your windshield clear, right? I should understand that the windshield is bothering you, and if I am the agent, I need to find a solution for you. The way it is working now is that you enter the car, you have a thermal problem, it is too warm or too cold, and you are expected to solve the problem for yourself. And what I'm saying is we can develop agents that they can solve the problems for you. Even more than that, what we see is that we are very different each one from the other. So the question is also more difficult because it's not just that I want to make a simpler interface. I want to actually understand your particular needs for the current context. Okay, so and in this case, this work was done in collaboration with Bar-Ilan University, with Professor Sarit Kraus and her students. So what we see here is that we will assume that our inputs to our agent are given by the dynamics of the vehicle, a set of thermal parameters. In this case, we have captured the target temperature, the fan level, air direction, external temperature, and in-cabin, the internal temperature in the car. And we also assume that I will know user preferences for his thermal comfort. And the goal of this agent would be to provide user comfort by proactively and intelligently adjusting the comfort level of the car. As I said before, the way we evaluate those systems is by quantifying the number of manual interventions that the user is required to perform to achieve that level he wants, and by maximizing driver acceptance. I want him to know that he's happy with the new system. Okay, so first of all, we talk about a need for having an adaptive interface that should be more intuitive than what we have today. So we have people that are different from each other, and we have the actual system, and we say this is very difficult. We should not be expected to understand all these dependencies. So the way we designed the first adaptive interface for this system is basically based on senses, on our senses. You tell me what you feel, and I will solve for you the problem. We ran 3 experiments. In the first one, we actually collected data from people interacting with this interface in order to understand what they really need. The second experiment is in parallel, so to have a formal model of how the thermal system works. And in the third experiment, we are going to evaluate the whole framework of the adaptive agent. So as I showed you before, that's the main framework. So now if I translate that to this problem, it becomes the agent should understand what is the current thermal state of the system, and it needs to understand what is the change in cabin temperature it is asked to achieve. It needs to know that for any change in cabin temperature, what are the parameters that will achieve that? That's the system model. We have from the user its thermal feelings or needs. And each time the user presses any button in my new interface, I also need to learn a user model that tells me how to translate those needs into what is the cabin temperature that I am aiming at. Okay, so as I said, we had 3 experiments. I will go shortly through them. In the first experiments, we brought 28 participants to our parking garage in General Motors in Herzliya. This particular experiment that I'm talking about here was just done for cooling conditions. We couldn't take the car outside, so it's a bit constrained, but I think the idea here is to tell you about the methodology that we are using. We collected data from all of these participants. So the way we did that is that people would tell us what are their inputs from our new interface, and they also would tell us what are the actual inputs they will give the existing system. So I could use that as a label for the inputs that the user was giving me. And finally, what we did for this particular cooling conditions when the car was parked is that we could learn a user model by linear regression, saying that given the current conditions, the agent could predict what is the next fan level desired, what is the next target temperature, and what is the next air direction, that is whether to the face, to the feet, or to both. The second experiment, as I said, we also need a system model. In order to learn the system model, I don't need the user at this moment. What I need is to work with the actual system in the car under many different conditions, and I will log the data referring to the internal temperature at time t and at time t plus 1, and then what could be the inputs by a user one time before. We collected 657 measurements, and finally we could deduce from this data, we learned again a linear regression model that could tell us with high accuracy, it's a 0.1 degrees Celsius, the accuracy, what is going to be the change in temperature in the next 15 seconds. We managed to compute the 15 seconds as a very small amount of time that is enough to get steady states for temperature. And then we also need to understand now that, okay, so the user will tell me what he needs. I understand that in terms of change in cabin temperature. I know how the system works. But now if I know the change in temperature I want to achieve, I need to know what actual settings to give the system to achieve that change. And the way we formalize is by looking at exponential decay time series, where each element in that series is a value for cabin temperature. So by having all cabin temperatures for some interval of time, I want my agent to learn the next value in that series. That's the way we represent the cabin temperature, where the parameters A, B, and C will be parameters that will be learned to adjust the temperature for you. So these are the personalization parameters. And the way that we learn these values is that at each point in this series, we will predict a value and then show the agent the actual value received. So the process is to minimize the loss between the actual value of cabin temperature and the one that it predicted, and adjusting, as you see in the algorithm, the parameters A, B, and C all the time in order to get that prediction even higher. And also by that, we achieve the personal adaptation of the user model. And then just to summarize this first domain, we had the third experiment where we had to evaluate the whole framework. So we brought 24 new participants to our parking garage in the summer. And the way the agent works was as following. First of all, if the user has something to tell us through the interface, then the user would touch that relevant button, and we will apply the user model to interpret what the user has input into the desired change in temperature. If the user didn't press on any button, then the agent will be running on a loop, and each time it will predict the next cabin change temperature, as we did with the time series, and use the system model in order to understand what parameters should be set in order to achieve that change. As you see here, the number of button presses that the user used in our experiment versus how many button presses the user used with a very similar to a normal existing climate control is much smaller, is significant statistically. So we had only around 5 times on average that the person touches the button as opposed to almost 7 button presses during a ride. It's also interesting to notice that we are not saying that everybody should like this adaptive interface. People are different. So there are people that actually like the technical interface, the one that you're used today, then that's fine. The only point I'm making is that not everybody has to like the same interface. And there are people that find it much more difficult to understand what's going on and what configuration it should choose. So when we ask people, we gave them questionnaires, of course, at the end of the experiment. So we see that 13 out of the 24 really very much like the adaptive interface, and 10 out of the 24 actually prefer the technical one. So this is not a small number, but still we see the difference. Besides that, we ask also to provide a score for using our adaptive interface. The adaptive interface got a score of 7.2 out of 10, and the normal climate control system just achieved a 6.2. So maybe these are not very high numbers. Maybe there is still a place to improve, but you can see the impact of this. So we were able to develop an agent that actually learned. So just to summarize these contributions, the adaptive interface was preferred by half of the people that were in our experiment. We were able to learn a user model that predicts what are the user needs given those inputs by this interface. And also, overall, we managed to have an adaptive behavior that can automatically and proactively adapt the system of the parameters of the climate control system to increase your comfort level and user acceptance of the system. So now we are moving to a second domain. I want to talk about personalized driving comfort. So the question is, why should we be talking about driving to be adaptive? And in a moment, you will see how also these two domains are very much related. The point is that when you look today at automated driving features, usually either they have only one default driving profile, meaning how the car should be driving, even if you don't tell it. And at most, it might have 3 driving profiles. Usually, if you have heard, you have comfort, normal, and sport. The point is that even if you have 3 profiles, and you might say, well, that's enough, because in our population, we might only have 3 profiles. That's OK. But the question is, where are those profiles coming from? Usually, these are engineered. These are calibrated by engineers. And I want to make the point that they are not taking human data-driven information. And I want to show you what would happen if we could adjust those driving styles to what humans might prefer. And as I said also before, for thermal, it all comes from the fact that we are humans. So we all know that users are humans, but we should be taking that into consideration when we program those agents and change their control actions. For example, in the driving context, You might have that experience if you sit next to a person that is driving. The person that is driving might be braking very hard, but he's fine with that. But the person sitting next to it might say, oh, no, don't drive that way, right? It's like feeling the difference between when you are behind the wheel and when you're not behind the wheel. Also, the environment might change your preferences for driving. Maybe speeds are okay when you're on an open road, but when you're making a turning, that might bring you to feel sick or it's too slow for you. So the question of this second part would be how we can learn those preferences of users for driving, and then how we can develop that agent that will adjust the control of the vehicle in order to support the level of comfort that you are looking for. So again, we did another set of experiments with another team, but from Bar-Ilan with Sarit Kraus. Again, we had as input the dynamics of the vehicle. We have a driving context that affected driving preferences and the user preferences. And now the goal would be to provide user comfort by interacting intelligently with our users regarding the driving settings. So I will show 3 experiments where we redefined human-centered driving profiles. We will learn how to predict when a user is not satisfied with the current driving style, and we will also learn how to adjust the vehicle control actions in order to fit what the user is looking for. Again, as I did before, the success criteria will be to quantify the number of interventions the user should be making in order to improve his comfort level, and the total driver acceptance from the whole interaction. So in this case, it's very difficult to run such an experiment on the road. So we did everything in a simulation environment. We have a car simulator. We have programmed our agents in a unit environment. If any one of you are aware of it, this is very known for kind of computer games. And you see there that our experimenter and the subject were sitting in actual car seats, and they were facing 3 big screens representing the actual car. So you could sit there and see like you were sitting inside the car, but the picture would be like a computer game. What we did in the actual simulator is we programmed a particular route in San Francisco, and all the graphics were real. So here you just see just the map, but the person would see in the screens actually like he was driving in San Francisco with buildings, traffic lights, and so forth. And the numbers that you see there is that because I assume that driving preferences are very much affected by the context, I just distributed the 11 events that I thought they will make a difference for people. And all these 11 events were tested in under 4 conditions. The difference between these 4 conditions have to do with the density of the, for example, parking cars, or the density of the cars in a traffic jam, or the number of pedestrians in a pedestrian crossing. So this should give us the rich environment of the driving situation. Now, regarding interfaces, we should understand first what is a driving style. So for thermal, we knew that it's about temperature, fan, and so forth. For driving style, it's not just the speed and the braking. It's not just acceleration. There are many parameters affecting how the vehicle actually drives. In Unity, when you program the car in this simulator, we have set a set of 10 parameters. They have to do with how aggressive you are pressing each one of the pedals, how aggressive you are when you start braking, how far you will start braking from a vehicle in front of you. So that vector of 10 parameters is for us the driving profile. And now the question is how we can ask those people what values they want for each one of those 10 parameters. So we've tested that in the beginning, and it seems that people can distinguish what is comfortable and what is not, and they can more or less understand the parameters. But obviously, it's not expected from us to be in the car and say 10 parameter values for each time that we are not happy with how the car is driving. And even more, even if they knew what parameter was affecting their comfort, they didn't know how to set the value, the number, the actual value of that parameters. So again, we designed an adaptive interface where we could put things in very simple ways. We also ran other studies, so we knew what people usually are used to tell about these parameters. And what you see here is that people could tell us only very simple inputs about increasing speed or decreasing speed, gap, and lane centering. And beyond that, we added the slider on top where they could just say, just drive sportier or calmer. Okay? But they didn't know how much sportier or how much calmer. In the first experiment, we learned, collected human data again, and we learned from that, the user model. We ran another, I will show the details in a moment, so I'll move faster. So in the first experiment, we brought 30 people to our simulation. We let them see, we let them experience the simulator by running a demo drive. Each person ran 4 times the same route with different conditions. And in this first experiment, we started everything with default driving profiles, one that we calibrated to be calm and one to be active. And then we get all the people inputs, and each time the person would choose some parameter to change. Our experiment had a set of rules how to change that in the driver vehicle. We got a total of 633 comments. On average, it will be 21. That's the number you should remember. I'll skip that. Also, in terms of usability, we got very good results for how people like the adaptive interface. That's the bottom one. So on average, it was a score of 3, the lowest, the better. And in terms of how good the agent understood your intention when you tried any one of the buttons and it did something, we got an average of a score of 8. In the second experiment, we took the data from the first one, looked how that driving behavior converged, and we clustered it. So those were the behaviors that the people preferred. We managed to receive, again, 3 types, like comfort, normal, sport, but now they were based on really human data. Then we brought another 30 participants. We ran the same experiment again, but starting with the driving profiles the people preferred, not the default ones. And now the number of comments dropped from 21 on average to 12, just by starting with human data driving profiles. And what you see here is we tried many different clustering methods in order to have all these driving profiles very much densely clustered in one cluster and far away from the other one. In terms of usability results, again, the adaptive interface got a low score as we desired, and the agent actually understood the user. This is just to show that really people are different. These are the 30 people, and these are the numbers of comments each one has provided. So it's not that most of us give only 4 comments, or all of us give 20 comments. Everybody gives many different comments. In the last experiment, and with that I will finish, what we wanted to have is to start with the same human-based driving profiles, but we also developed the agent that was able to predict when a user is going to be unsatisfied with the driving style, and then also it learned how to adjust the settings for those settings so that the person would avoid entering an input because the agent will know beforehand how to set those settings. We brought another set of 34 people, and we ran the agent. And as you see, we learned first to predict when the user is unsatisfied by trying different neural networks systems, and we ended up choosing the convolutional neural network with the highest AUC. And as you see here, the number of interventions from the user is even lower. So if we started with 21 on average comments on average for a case where people were given default driving profiles, we dropped the 21 on average to 12 on average when we let people choose a human preferred driving style. And we even got to 7 comments on average when the agent was able to learn and to predict when that person is going to be not satisfied. What is interesting here on the right is that the agent, as you see, was correcting many more comments. So the user was not inputting them, but the agent did know that it has to change. And so eventually the 7 comments on average that the user still did is those corrections that it did to the agent, because the agent is not perfect. Okay. Just to summarize, what you have seen here is our framework for adaptive agents, so that we can bring together human factors, human-machine interactions, and machine learning methodologies. We believe that we need to learn human preferences and know to understand when people are with discomfort and interpret that into system action and control. And by that, we will achieve higher levels of user acceptance and better utilization of automated driving. Thank you.